Uh, Hello everyone. So DC, right? In the communication lab, the digital communication part is what we're talking about. Next experiment that we're talking about is pulse coded modulation, or simply called as PCM. So what's the deal with pulse coded modulation? See, if at all you with so many advantages told to you about going for a digital communication, that means it's always good to send ones and zeros, which are very much easier for you to predict the presence and absence with all those advantages of digital communication being present. So how are you going to do it? So here is the method. So the method entire thing process is called as a pulse code modulation. And how do we do this particular thing? So let us try and understand. So the process includes this thing, sampling, quantization, and coding. Okay, sampling, quantization, and encoding. Source encoding is what we call it. Okay, source encoding or channel encoding. Which is this encoding, by the way? Think about it, whether this encoding is a source encoding or channel encoding. Okay, till then let us try to understand. So the first part is sampling. So if at all you have this particular analog signal, so how are you going to sample this particular thing? So it is should be, it should satisfy sampling theorem. What is sampling theorem? Sampling frequency should be greater than twice the maximum signal frequency. Less than that is going to cause aliasing. More than that doesn't hurt. Maybe a large amount of memory. Okay, maybe a large amount of memory and too much of processing time. Depends on your requirements. Okay, so first thing is sampling. So when you do sampling, what's going to happen? This entire continuous time thing, the infinite number of samples, are now going to reduce into finite number of samples. The first problem is solved. So that means now you are ready to, for the values are finite, they can be stored and they can be processed on a digital computer. Next thing is the amplitudes are still infinite. You can see, just as the x-axis was continuous, even the y-axis, because of continuous values, it was also having infinite number of samples. So here also infinite number of samples need infinite number of bits for representation. If at all I have 2 bits, how many values can I represent? 2 to the power 2, 4. If at all I have 8 bits at my disposal, how many bits can I, how many levels can I represent? 256, right? 256 levels. So you can see here now the number of levels here are something like 7, 6, 5, 4, 3, 2, 1. So how many levels are this? 0 to 7, then minus 7. So totally some 15 levels. And for representing 15 level, make add one, maybe 16 levels. You can manage it only 4 bits. Okay, for 16 levels you need 4 bits. For 256 levels you need 8 bits. In case you happen to have infinite number of amplitudes, then you may need infinite number of bits for storing. So that's not done, right? So that's why the second step, quantization. So sampling converts the infinite number of samples, time samples, into finite number of samples. Quantization converts the infinite number of amplitudes into finite number of amplitudes. And then comes the encoding part. Now once you have done the quantization, the next part is converting them into ones and zeros. Okay, converting them into ones and zeros. Then there we are ready for the pulse code modulated data. Okay, so what are we going to do here? By the way, what are we going to do? So we are just going to take any analog signal, and then afterwards we will decide on how many number of samples to be taken. Okay, what should be the sampling frequency, that we will decide. So sampling frequency, will keep it simple. Okay, it should be twice the maximum signal frequency or much more than that, doesn't hurt. Then afterwards we'll tweak into this quantization, how many number of bits. So depending on, if at all you want you allocate 5 bits, you can get 2 to the power 5 levels. If at all you allocate 10 bits, you can get 2 to the power 10 levels. So n numbers can be set. Then afterwards simply encode it, and then afterwards do the entire reverse process and see a demonstration of that. So now let me take you to a matlab here. Now let me take you to matlab towards that program. Okay, so here is the program. So what has been done here, you can see a fairly simple program has been taken. Some frequency, you can understand this particular thing. Okay, see here, sampling frequency of 100 has been taken, some signal of amplitude, 5 volts plus 5 to minus 5 has been taken, and you can see a bias has been added because I wanted it to be a completely positive values. Okay, that's what in my situation you remove this, you can get negative values also, but the kind of logic that I have used, I have taken only positive values. Okay, in this particular program. Okay, so then you are free to use any kind of program. So this one is completely DC. Okay, then what we'll do is, so what we'll do is we'll round the value. Okay, so what is meant by rounding the value? So that means if at all round means if at all I have 4.4, and if at all I have 4.6, and if at all I have a 5.2. So two things, three things you can do. Okay, so sometimes you have to take decisions. How are you going to do it? If at all there is 4.4 can be rounded. So if at all I have a value in between, from in between, say this is 4 and this is 5, you have several options. There is something called as midrise quantization, something called as mid-thread quantization, and then there is something between. So if at all you get something like 4.4, okay, so what would you say? Maybe I will round it to 4, and if at all there is something like 4.6, maybe this I will go to saying to 5. Okay, so the percentage error, how much things can get worse here? You can see the error, maximum error you will get is 0.4999, right, which is going to happen when you have 4.99, 4.499, which you will round it to 4. Okay, and a 5.00001, which you will round it to 4.5111. Okay, 4.5001, which will round to 5. That is the kind of quantization error that you are going to get. Fine anyway, but by doing this, now we can manage with very less number of samples. So this here, the rounding process is my symbolic representation of quantization. Okay, so this is my representation of sampling, where I chose a sampling frequency. 100 has been chosen by me. You can take any number. It should be greater than 4. That's it. Okay, 100 looked good, I thought, on screen. That's why 100 I took. Okay, so the first, this is the thing with sampling. Okay, this is first is sampling. Rounding, whatever I did, is a symbolic representation of my quantization. Then afterwards coding, how I'm going to do coding? I will simply use this particular command here, decimal to binary. I have used this function decimal to binary to convert the data from into ones and zeros from the decimal values whichever I got. Okay, so that is my coding. Okay, so sampling, quantization, and coding. Okay, a symbolic representation of those has been used here. And then for the recovery, what do I do? um, you can see for recovery also I have done here. I had did the decimal to binary, here binary to decimal I'm doing. And then I will also do this modulation, just to indicate how things are happening. Okay, just to indicate how things are happening. And once again here, once I get a data, it will be there in a string. You can see BRI, the binary data, is actually a, it's actually a two-dimensional thing because with all the values. So I will reshape them. I have reshaped them to get the actual one-dimensional sequence, okay, of ones and zeros. Then modulation to indicate, right, this is the step, right? Sampling, quantization, code, and then afterwards modulation, something like BPSK, QPSK. So here we have used PSK only. Someday we have, which PSK we have used, by the way? PSK modulation 2. A BPSK has been used symbolically, and then the reverse process. Now let us run the program. Let us wait for the output. Yes, here we got this particular thing. I don't know how is this interface looking for you. Okay, so here is the symbolic representation. We started with these things. The values were sampled, okay, as indicated here, and you can see the values have been quantized. Very limited number of values here, very limited number of values that we got. Then afterwards all these values were converted into binary to decimal to binary and converted into one dimensional data. You can see 100 samples, right? And nearly 100 samples converted into around how many? Around 400 number of bits here. Okay, around 400 number of bits here. Actually, I was expecting a number 500. Okay, 5 bits were used. Maybe only a few have been taken, remaining have been removed. Fine. And then afterwards, the reverse process, PSK modulation, then demodulation, and here what we have got. Okay, so did you get the original way by the way? No, 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 we did not get the original way. We sampled it, right? Had we taken more number of samples, had we allocated more number of bits, things would have been better. But we chose to make a compromise in the, we wanted finite number of samples, finite number of bits per sample. So this is what's going to happen. But then a programmer can always choose, an engineer, a communication engineer can always choose how many number of bits. Okay, so you can change in the program. You can go make suitable changes in the program and just to uh, have a feel of it. Okay, so that is pulse code modulation. Okay, so as I told you, I will share this program also with you. Okay,